In the last video, we saw how the deformation gradient f can be decomposed into a rotation and a stretch. This is called the polar decomposition, and how this triangle gets stretched to this triangle and then rotated to this triangle. Let's explore this stretch matrix U some more, using its eigenvalues and eigenvectors. Before we can do that, we need to know a little bit about what eigenvalues and eigenvectors are. We'll just say a little at this stage, and then we'll take this up more in assignment 4. So what are eigenvalues and eigenvectors of a matrix? In general, when a matrix operates on a vector, it both rotates the vector and changes its length. So for example, let's take a random vector and multiply it by u and see what happens. So we see that this is the original vector, and this is what happens to it when you multiply by u. And in general, this vector has both been rotated and its length has been changed. But some matrices have associated with them special vectors called eigenvectors, such that when these special vectors are operated on by the matrix, they are not rotated, but only their lengths are changed. For example, if v is an eigenvector of u, then u times v is simply lambda times v, a scalar times v. So v is not being rotated, but its length is being changed by the factor lambda. And that factor lambda is called the eigenvalue. So since U is a 2 by 2 symmetric matrix, it has two separate eigenvalues. This is not true of all 2 by 2 matrices. U has two separate eigenvectors because it's a symmetric matrix. And these eigenvalues and eigenvectors can be computed using the eigen function in MATLAB. So you have access to this live script, and you should kind of experiment with it yourself as well. So the eigenvalues are shown here, and the eigenvectors are shown here. The eigenvalues of U are both positive. That tells us that the matrix U is positive definite, which means that the matrix cannot squish a triangle into itself because it's positive definite. The matrix cannot squish a triangle into itself and flip it over. It can only stretch it. So the figure below shows a small circle with the eigenvectors of U marked. So the red line here and the green line here are the eigenvectors of U. Now if we apply U to this circle, its shape gets changed into this ellipse. As you can see, the red line is not rotated, but only changed in length. And the green line is not rotated, but only changed in length. So essentially what the matrix U does is it takes a circle and turns it into an ellipse while preserving the directions of two special vectors called the eigenvectors. We'll see in the next video that we can use this idea to motivate the definition of strain in 2D.